Hi, my name is Oscar de Groot. I'm a PhD student of the Delft University of Technology. In this work, I'll talk about our work on globally guided trajectory optimization in dynamic environments. An idea of this work is that we improve optimization-based trajectory planning by using global guidance. In fact, we have two components in this planner, where the first is a high-level component that computes distinct global trajectories in the dynamic space. And we use this to guide a local optimization-based trajectory planner. And in this work, we show that the combination of a high-level planner and a low-level planner help to improve task times and reduce collisions in certain cases. The setup that we consider is the following. We have a robot that is a mobile robot, and we have several humans in the environment that form dynamic obstacles that the robot must avoid. And the goal of the robot is to reach a goal in space. And usually this problem is solved via a model predictive control problem, where we formulate as the objective to reach the goal under some robot dynamics, for example, a unicycle model. And then we formulate collision avoidance constraints that specify that the robot and the humans must not overlap in their collision areas. Now, unfortunately, because the space in which a robot can plan is non-convex, this solution or this program itself is locally optimal. And the solution to the optimization is locally optimal. And this can result in bad behavior. For example, in this slide, we have two cases where on the left, two pedestrians are walking towards the robot. And because the robot is initially planning to go between them, it becomes infeasible and cannot continue. On the right, we have a crowded case where first we see that the regular planner can switch a lot between different plans. And additionally, with this red obstacle, we see that even when it finds a good solution, it's still not the best solution that it can find. It could have passed below the red obstacle. In this work, we consider how we can guide the local optimization. And our idea is based on the guidance planner that was introduced by Zhao et al. In a related work, where they used visibility probabilistic roadmaps in addition to topology comparison function. And the idea of the topology comparison function, in this case UVD, is that we can distinguish between different types of trajectories. For example, if here we have the blue and the green trajectory, then we see that there is an obstacle between them and they are in distinct topologies. We then can keep both. But maybe if we find the blue and purple trajectories, we find that they are equivalent and we only have to keep one. And that way we can filter out trajectories that are in distinct topologies. Now in that work, it was used to compute trajectories under 3D static obstacles for drone flight. In this work, we consider instead to use the same methods, but for 2D and dynamic obstacles. The idea is that we look at this workspace not only in space, but also in time. Here on the right, we have the 3D representation of XY space and time in the vertical axis. And by computing topology distinct guidance trajectories in this 3D space, we find different types of driving behaviors. For example, passing left and passing right. And we also find paths such as speeding up and slowing down to avoid both obstacles. The idea is that we find the best option of these driving behaviors and use it to guide the local planner. We now present several results that we obtained. First, in the real-world case, we have on the left here camera feed and on the right the visualization of the methods. And what we visualize is the graph that we construct using the visibility PRM method. And we show the guidance trajectories that we compute with this. And usually there are more than one, each identified by a different color. And we show what the local motion plan is doing, which is this model predictive contouring controller. In the first experiment, the two pedestrians are crossing. And we see that the robot is able to pass behind the second pedestrian, even though it first plans to go in front of it. And this shows that it can escape a local optimum. And we also show that even with the pedestrian moving straight towards the robot is able to find a safe path around it. Then in simulation, we also verified the results that we previously showed, where, for example, if two pedestrians are walking towards the robot, it's now able to navigate around it using this guidance. And in the crowded case, we find that the planner is more stable. And also that instead of passing on top of this red obstacle, it now passes below, showing that it navigates more faster through environments. the quantitative results that we found is that in this head-on case, the local motion planner almost always collides, while the guided planner never collides. If we look at several random scenarios with an increasing number of pedestrians, 4, 8, and 16 pedestrians, we see that on average, we reach the goal faster than the local planner. And interestingly enough, for some cases, the computation times of our methods is lower than the local planner, even though we also compute the guidance plans at first. And this might be related to the fact that the guidance helps the local planner to find a solution faster. And this concludes our work. We hope to see you at ICRA at our poster. Thank you.